Blob versioning in Azure Storage is a foundational feature that allows administrators to maintain a complete history of object changes within their storage accounts. Whenever a blob is modified, a new version is automatically created, preserving all iterations of the data. This approach is particularly relevant for scenarios where regulatory considerations or compliance requirements necessitate the retention of historical data. By enabling versioning, organizations can effectively track and compare various instances of a blob, retrieve past states, or recover from accidental overwrites. In the broader context of Azure Storage Management and Governance, versioning integrates seamlessly with soft delete, access policies, and other robust security mechanisms to offer a multi-layered data protection strategy. In this module, the focus rests on configuration steps, operational implications, and best practices to ensure that versioning aligns with organizational retention goals and performance considerations without introducing excessive overhead. Understanding these aspects will help administrators design storage solutions that both preserve data integrity and optimize operational practices. At the heart of blob versioning is the concept of maintaining distinct snapshots each time a blob undergoes change, ensuring that older data remains accessible. This approach serves multiple purposes. For compliance-driven workflows, versioning offers traceability, enabling detailed audits that identify exactly when and how data changed. Additionally, operational workflows benefit from quick recovery of specific file versions, minimizing disruptions after accidental deletions or file corruptions. Integration with other Azure services, such as lifecycle management for automated data movement and retention schedules, elevates the utility of versioning beyond mere backup functionality. By leveraging versioning, organizations can address a variety of data protection requirements, from safeguarding highly sensitive information to maintaining iterative design processes across large development teams. These benefits underline the pivotal role of versioning when designing robust cloud storage environments, where data continuity and retrieval efficiency are core objectives. Activating blob versioning in Azure requires a simple but intentional process that can be completed through the Azure portal, Azure CLI, or PowerShell. Initially, administrators navigate to the relevant storage account within the portal, locate the data protection blade, and enable blob versioning. This setting ensures every subsequent change on blobs within that storage account triggers the creation of a new version. For command line enthusiasts, the Azure CLI offers a straightforward approach using commands such as AZ storage account update with the enable blob versioning parameter. Similarly, PowerShell scripts achieve the same outcome through specialized cmdlets, thereby accommodating a range of deployment preferences. Once enabled, versioning applies to all existing containers and newly created ones in the account. This universal application streamlines administration and reduces the risk of incomplete coverage. Careful planning around associated storage usage and compliance requirements is advised before enabling versioning in production environments. Once versioning is active, administrators and authorized users can list, view, and restore historical blob versions as needed. In the Azure portal, the Blob Properties pane displays a Versions tab, where each modification is time-stamped to facilitate identification and retrieval. Restoring an older version typically involves overriding the current active blob or copying it to a newly named object, thus preserving both instances. Developers using the Azure Storage SDK can programmatically list versions by specifying the appropriate parameters in their API calls. This programmatic approach proves especially valuable for automated tasks or advanced data workflows. While version blobs are seamlessly accessible, permissions remain subject to the same role-based access control, RBAC, or shared access signatures previously configured in the storage account. Consequently, versioning neither bypasses nor diminishes any existing security and governance measures. Instead, it works in concert with these frameworks to enhance data protection. Blob lifecycle management extends versioning by automatically moving or deleting older versions based on defined policies. Administrators can create rules specifying which versions of a blob should transition to cooler storage tiers, such as Cool or Archive, optimizing cost efficiency. Lifecycle policies can also enforce deletion schedules for versions exceeding a certain retention threshold. For example, an organization might keep versions active for 30 days and then automatically archive them for long-term storage. By combining versioning and lifecycle rules, data remains both protected and cost-effective, ensuring that frequently accessed versions stay in hot tiers, while rarely accessed iterations are moved to lower-cost options. These rules are configured using either the Azure portal or resource management templates and can be applied at a container or storage account level. Through this integration, versioning becomes a dynamic strategy that not only retains data, but also manages its distribution and longevity in accord with organizational policies. Soft delete and blob versioning form complementary layers of data protection. Soft delete retains a copy of a blob even after it has been deliberately removed or overwritten, allowing recovery within a configurable retention period. Meanwhile, versioning preserves every iteration of the blob throughout its life cycle. When both features are enabled, organizations can recover earlier versions even if accidental deletions occur. This integration implies that once a file is deleted, older versions remain accessible during the soft delete retention window, preventing permanent data loss. In regulated environments requiring documented data retention, having both versioning and soft delete significantly mitigates risk. Implementation is straightforward. After enabling versioning in the Azure portal, administrators can navigate to the data protection pane to confirm or configure soft delete settings. Organizations often combine these features with additional measures like encryption and firewalls to create a robust, multi-tiered defense strategy that secures data across various failure scenarios. Whether through the Azure portal or via command line tools, managing blob versioning is streamlined and efficient. Within the portal, the interface provides straightforward toggles for enabling and disabling versioning, along with companion features like soft delete and lifecycle policies. The relationships between these options are visually highlighted under the data protection blade, simplifying the administration process for less CLI-savvy users. For the command line approach, Azure CLI commands such as AZ storage account update enable advanced users to configure versioning at scale. Organizations can incorporate these commands into infrastructure as code pipelines, ensuring versioning settings are consistently applied across multiple environments. Likewise, PowerShell templates, such as set as a storage account, facilitate integration with automated scripts, catering to Windows-based administrative workflows. By understanding both methods, administrators can choose the most suitable approach for their operational constraints, seamlessly blending manual oversight through the portal with powerful scripting capabilities for repetitive or large-scale tasks. Automation plays a vital role in maintaining version control at scale. Through Azure Resource Manager templates, teams can define standardized configurations that include versioning parameters, soft delete, and lifecycle rules, ensuring consistency across multiple storage accounts. A typical template might declare the storage account's properties, specify the desired versioning state, and integrate tier transitions or deletion schedules for older blob versions. This approach accelerates deployments and reduces the risk of misconfigurations, particularly in environments where quick provisioning is essential. Further automation opportunities arise with Azure PowerShell and Azure CLI scripts, which can be scheduled or triggered through Azure Functions or Azure DevOps pipelines. These scripts can handle tasks such as scanning for outdated versions or moving them to archival tiers once they surpass a specific age. By systematically orchestrating these processes, organizations establish a self-sustaining data protection scheme that dynamically responds to changing business and compliance demands. In scenarios involving large data sets, versioning can significantly impact storage costs and operational performance. Each modification generates a new data instance, potentially leading to an extensive volume of stored versions. Strategic design is therefore critical. Administrators can employ lifecycle policies to transition rarely accessed versions to more affordable tiers, thus reducing the financial burden. Additionally, Implementing indexing solutions or metadata tagging helps keep track of critical versions, expediting retrieval. For high-throughput applications that modify blobs frequently, a carefully designed workflow is essential to avoid performance bottlenecks. Splitting large files into smaller segments or employing append-only strategies can limit the overhead associated with versioning. The combined use of analytics tools, such as Azure Monitor and Azure Storage Analytics logs, provides insights into usage patterns, allowing administrators to optimize retention periods. When planned thoughtfully, large-scale versioning ensures data remains protected without imposing prohibitive storage costs or complexity. For secure blob versioning, administrators must align retention strategies with established governance frameworks, such as Azure policy or internal compliance mandates. Role-based access control, RBAC, configurations should only grant modification privileges to authorized personnel, thereby reducing the likelihood of unintended overwrites. Additionally, encryption at rest is automatically enforced for all blob versions when enabled at the storage account level, ensuring each iteration remains protected from unauthorized access. Pairing versioning with advanced networking configurations, such as using private endpoints and virtual network service endpoints, enhances isolation from public internet exposure. Periodic audits of access permissions, combined with multi-factor authentication for privileged users, further tighten security. In some contexts, integrating the feature with real-time threat detection in Azure Security Center provides alerts on suspicious access patterns. By layering these measures, organizations ensure that enabling versioning does not inadvertently create new attack vectors or compliance vulnerabilities, but instead fortifies their overall data protection posture. Although blob versioning offers robust data protection, it is accompanied by certain constraints that warrant attention. Firstly, versioning stores copies of each changed blob, which can accumulate quickly in dynamic environments. For datasets undergoing frequent updates, storage costs and compliance overhead may rise substantially. Additionally, versioning only applies to block blobs. Page and append blobs are currently excluded from this feature, limiting its applicability in some scenarios. Interoperability with third-party backup or archive solutions may also be restricted if those solutions are not fully aware of Azure's versioning mechanics. In multi-region deployments, replication ensures that each version is copied across designated regions, potentially increasing replication costs. Also, older versions are not automatically purged unless lifecycle rules are configured, making it critical to implement a well-structured policy from the outset. Being cognizant of these limitations helps organizations weigh the benefits against the associated costs and complexities. Monitoring the utilization and costs of blob versioning is inseparable from effective storage governance. Azure Monitor and Azure Storage Analytics logs provide visibility into the frequency of blob modifications, the number of versions being created, and overall storage consumption. Through these metrics, administrators can detect anomalies, such as unexpectedly large spikes in version count, which might signal unauthorized activity or poorly designed data workflows. Cost management features within the Azure portal offer aggregated views of storage expenses, enabling teams to forecast budget allocations and adjust lifecycle and retention policies accordingly. Additionally, resource tags can be used to differentiate version-related costs from other storage expenditures in multi-team environments. By establishing regular reviews of these usage reports, organizations can fine-tune their versioning strategies, ensuring ongoing alignment with performance and financial objectives. Effective monitoring thus acts as both an early warning system and a strategic planning tool, maintaining control over versioning expenditures. In practice, blob versioning addresses a variety of industry-specific challenges. In software development, continuous integration pipelines often exchange build artifacts, configuration files, and other key assets with each commit. Versioning ensures that developers can revert to a functioning build in case a regression or bug arises. Healthcare organizations benefit from preserving patient records or research data while maintaining compliance with data integrity regulations, thereby meeting stringent audit demands. For media and entertainment, versioning is valuable when editing large video or design files to retain historical snapshots, enabling creative teams to compare revisions seamlessly. Financial institutions utilize version logs for transaction auditing, ensuring that critical information remains recoverable, even amid frequent updates. These diverse scenarios illustrate the significance of blob versioning beyond mere backups. By systematically capturing historical states, versioning enables enhanced collaboration, robust auditing, and resilient operations across a spectrum of complex, data-centric environments. Once comfortable with the fundamentals of blob versioning, the logical progression involves integrating this feature with broader Azure ecosystem tools. For instance, linking version containers to Azure Data Factory or Synapse analytics pipelines can streamline data processing while retaining historical iterations for analytics. Pairing versioning with event-driven architectures, such as Azure Event Grid, extends automation potential. Triggers can fire whenever a new version is created, initiating tasks like indexing or backup verification. Considering advanced governance, Azure Policy can enforce mandatory versioning on all new storage accounts, ensuring consistent best practices across the organization. Future optimizations may include deeper integrations with AI-driven solutions for anomaly detection and version creation, adding predictive capabilities that enhance overall reliability. By continuously exploring these integrations, teams expand their data management toolkit, unlocking new efficiencies and insights while preserving the strong base of data protection and recoverability provided by blob versioning.